Okay, so this is the second part. This is kind of the meat of all of this. We're going to start defining what an atom is, okay? And we're going to start with the atomic number. So an atomic number is going to be defined as the number of protons in the nucleus, okay? We call that the atomic number, that is Z, okay? It defines the element. Okay, so the number of protons or the atomic number is going to tell you what atom you have. Okay, so carbon has an atomic number, a Z equal to 6, an atomic number of 6, meaning it has 6 protons. Every single atom with 6 protons is going to be carbon. Okay, any atom with 6 protons will always be carbon. Okay, sodium. Okay, hydrogen has 1, and these go in order, and we actually see this down a little bit further. But the atomic number, the Z, is going to be defined as the essentially as the atom or element that it actually is. So I think if you scroll all the way down to the very end, and we're going to come back up, but if you scroll all the way down to the end, you do have a periodic table, and we're going to use this. But when you're looking at a periodic table, the whole number that you see defines the Z value. So carbon has a Z value of 6. So it has 6 protons in its nucleus. Sodium, 11. Aluminum, 13. Chlorine has 17 protons in the nucleus. Okay, so just recognize that this whole number, and it can be in different locations depending on your periodic table, okay, it's going to define what the thing actually is. Okay, so it's really important that we understand that a atom is defined by its charge. And in fact, when we created the periodic table, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, we just keep going with the atomic number, okay? And the locations, copper, iodine, bismuth, sodium, all of these things are going to have different properties because they're different elements. They have different protons in the nucleus. Next up, the atomic mass number. The atomic mass number is defined as the number of protons plus number of neutrons in the nucleus. Okay, so those two things together are going to give me the atomic mass. All right, so the nucleus is composed of 2 parts, protons and neutrons, and that's going to give us the total atomic number or atomic mass, or A, of this. So if I take a look at this compound here, or this little example I have here to the left, we are going to have this representative of really what we have. So again, Z is the atomic number, A is the atomic mass, and the X is the chemical symbol. And so let me define all of these. Again, A is going to be atomic mass. Again, atomic mass is protons plus neutrons. The Z is the atomic number, which is just simply the protons in the nucleus. And then the X is going to be the chemical symbol. By the way, these two things are always going to be linked. Z and the X are always going to be linked because having 6 protons in the nucleus makes it carbon. So 6, atomic number of 6 equals atomic symbol of carbon. If I say you have carbon, you have 6 protons. If you have 6 protons, you have carbon. Those two things are always going to match, okay? In fact, we don't even have to say the atomic number if we know what element we have. Or we don't have to say the symbol if we know how many what the atomic number is. So with that said, if you count this, what we see is 1, 2, 3 protons in the nucleus. So that means my atomic number in this example here is 3. Okay. Well, if we go back to our little periodic table, 1, 2, 3, that means that this is the atomic number of 3, making it lithium. So what we have down here is if I have an atomic number of 3, that means that this chemical symbol is going to be Li, or lithium. Okay. And then finally, the atomic mass, we have to add up all of the particles that are in the nucleus. We don't care about electrons, we just care about the nucleus. So what I have is I have the, again, the 1, 2, 3 protons plus the, so 1, how am I gonna do this? Here we go. 1, 2, 3 protons and 1, 2, 3, 4 neutrons for a total of 7. 1, 2, 3, 4, 5, 6, 7 total particles in the nucleus. So there are 7 total particles in the nucleus. The atomic mass is going to be 7. So if I were to rewrite this thing, it would be 7. I'll put it elsewhere. Here we go. 7, 3 Li. That defines the element and what it is. The last little bit of this is I'll say up here, this is going to be our charge. This is going to be the hardest one to get because it feels the most awkward. This is always going to be protons minus electrons. Okay. So in this case here, I have 3 protons minus, notice I have 3 electrons around the outside. The total charge is 0. So there's a couple ways I can represent it. If I don't put anything, there is no charge. Or if I put a 0 there, that indicates 0 charge for that lithium. Okay, so I could put a 0 here as well. But, well, actually, I'll do that. So 0 here, but this is the same thing as this. You can put a 0 there, or you don't need to. Okay, great. So we are starting to understand the nucleus. We're going to get more. We're going to do a bunch of chemical symbol experiment or demonstrations below, but that's a good start. So let's talk about the subatomic particles that we're seeing. So protons, abbreviation, there's a couple of ways you're going to see this. Just simply a lowercase p or a 1H0. That is another version of a proton. None of that matters as much as the relative charge. All protons have a charge of +1. Okay, for all intents and purposes, the charge of proton is +1. And it has a relative mass of 1, we're going to say AMU, which is just basically saying 1 proton or neutron. It's the definition below you see, because the difficult to express how much is in a gram, we just say just 1 particle. Okay, so we're just going to say 1 thing in the nucleus, 1 atomic mass unit. Neutron, N or N10, again, we don't really care so much about that, doesn't have any charge. It is neutral, and it has a mass of 1 AMU. Okay, so this is a great start. Charge of a proton, neutron, mass of each of these as well. Okay. There we go. So protons are +1, neutrons are neutral, and an electron has a charge of -1. By the way, an electron you're typically going to see just E-. So relative charge of an electron is -1, but it actually has no mass. It's like, well, we'll see that below, but it's like 1/10,000th or 1/1000th of a neutron or proton. So it does not matter in comparison. So what we notice is, again, these two things here, this is where all the mass is coming from. Protons plus neutrons. Okay, those two things together give me the atomic mass. But the charge, the two things that have the charge are the protons and neutrons. So that what that means is we have charge equal to protons minus electrons. And that's going to give us the overall charge, and we'll talk more about that in just a moment. Okay, So those are the important parts. If you actually look, why do we use relative? Again, the idea of relative mass and relative charge. That's because if you actually look at the actual charge of these things, they're really tiny. 1.6 times 10 to the negative 19, or negative 1.6 times 10 to the negative 19, or masses times 10 to the negative 24. Okay. And what you notice is a proton. Actually, I think these are backwards. This is supposed to be up here. Yeah, I've got to fix that. Those two are supposed to be reversed. But again, you get the idea. In fact, I can just ignore that because the actual mass in atomic mass units is very different. Okay, so yeah, those are backwards that I can tell. Okay. Okay, so with all of that said, a neutron has no charge. So we have a bunch of atoms with different stuff in them. Okay, and so if we take a look, let's talk about the idea of an isotope. And this looks more complicated. Protium is just simply a hydrogen with one, this 1,3, and deuterium 1,2. That is the definition of those three right there. An isotope is simply same number of protons, which means same element, different number of neutrons. Same element, different mass. Okay, so what I have here are, notice that every single one of these is hydrogen, but they all have different masses. Those are three different isotopes of hydrogen. Okay, when we see these isotope symbols, we can write in a bunch of different ways. So I can represent this as 2H, that's deuterium, okay? Or I could say hydrogen 2, that tells you the mass as well. If you see a number, it's always the mass because it never, ever is the atomic number, because the atomic number, we know what it is. If it's hydrogen, I know it's 1, okay? So yeah, so that's what we're looking at. Hydrogen, you see that the superscript there, 2, or we could also say H2. That's an example of hydrogen 2, or hydrogen with an atomic weight of 2, or a mass of 2. Okay. All right. So isotope, this is the important part. Same element, different mass. So I could say carbon 13, carbon 12, nitrogen 14. These two are isotopes. This one is not. Okay, isotopes have to be same element, different different masses. All right. So number of electrons in a neutral atom. So remember, the number of electrons in a neutral atom has got to actually, so electrons are this negative charge. So all of these protons are positive. So if I have 10, the number, if we want a neutral atom, that means that I have to have an equal number of electrons and protons. Okay, so they have to equal one another. So if I have a nucleus with 10 positive charges or 10 protons, that means that around the outside, I need 10 electrons as well, right? Because those 10 electrons are negative. So the 10 plus and the 10 minus, overall, the charge is going to be equal to 0. So it's going to make it neutral. Okay. So with that said, let's do the first example here, and we're going to do the rest in class together. So if I have iron, if I have this symbol right here, Fe is iron, how many protons, how many neutrons, how many electrons? I know that iron has 26 protons. And because there is no charge up here, that means it's neutral. That means it's going to have the same number of electrons. Now, how do I figure out how many neutrons it has? 55 minus 26. Okay. Okay, so how many is that? 30, 29, is that right? Yeah, so neutrons is, oh my God, I can't do math right now. 24 would be 50. Yeah, right, 29. So there are 29 neutrons in the nucleus, okay? Again, the total mass equals protons plus neutrons. The atomic number is just simply the protons, and there we go. So if I have lead 207, how many protons, neutrons, and electrons? What is the symbol for this? Or recreate one of the symbols from above. Okay. All right. Good. Um, so the next little bit, we're going to talk about fractional abundance. So we have all of these different elements with different amounts of protons, electrons, neutrons, and all of that. And we're learning how to write these symbols. Okay. And in fact, we're going to do a handful of other examples as well. So let me include those here. I'm just going to come up with a few, and then these are just going to pop up for you guys, but I'm going to come up with a couple, and then I'll probably end the video and I'll share another one, because this is important stuff and it's getting a little more confusing. So these should pop up for you instantaneously. Okay, so here are all the examples. You can go ahead and pause it. How many protons, neutrons, electrons, and what element are we talking about? Protons, neutrons, electrons, and what element are we talking about? There's a couple of tricky ones in here, and you have to recognize, so I'm just going to do one example out of all of these. So let's take a look at, let's say, fluorine. Okay, so if you look up fluorine, we see that fluorine has an atomic number of 9. Those two things, fluorine is 9 protons is fluorine, okay? So that's the extra information that I need. So how many protons? It has 9 protons. How many neutrons? Well, 19 minus 9 is going to give me 10 neutrally charged particles. So the total mass is those two things combined. Electrons, how many electrons are in the nucleus? Well, what we notice is we actually have a charge equal to -1. So what we have to think about is I have 9 positive charges in the nucleus. If I had 9 negative charges, the whole thing would be neutral, would be 0, okay? I cannot change the number of protons in the nucleus, right? So if I did this, 9 minus 9 is equal to 0, right? But if I did 9 minus 10, there is, what this negative charge is telling me is there's 1 extra electron, right, to give me a -1 charge, meaning I have 9 would be neutral. I have 10 electrons around the outside, right? So the charge is going to tell you how many extra electrons that you have, right? You can only lose and gain electrons. You cannot change the protons. So in this case, fluorine has a -1 charge, so it has 1 extra electron. It has 1 extra negative charge. Sodium, on the other hand, is a positive. So what that means is sodium has not 1 more electron, which is negative, but it has 1 fewer electron. So we've lost an electron, okay? Phosphorus has a 3- charge. That means that however many electrons in a neutral atom, add 3 to it, because I've got 3 extra present. So if you have a negative charge, this silver here has a +1, meaning it has lost 1 electron, okay? And so I'm going to leave you with this mnemonic, or this ability to remember. I'm positive I lost an electron. So it becomes more positive, or if it's positive, it's lost electrons. If it's negative, it's gained electrons. I'm positive I lost an electron. Okay, so that is a good place to stop for this. And there's going to be another one on a little bit more complicated thing, which is the isotope stuff.